So today we're going to be looking at an example of how we actually use the Fick's law. Okay, so in this example, the question is saying that we have a mixture of helium and nitrogen gas is contained in a pipe at 298 Kelvin and 1 atm total pressure, which is constant throughout. At one end of the pipe, at point number 1, the partial pressure, so PA1 of helium, so we can also label here helium as A, and the other one, our nitrogen as B, right? So the partial pressure of helium, which is known as PA1 at point 1 is 0.6 atm, and the other end 0.2 meter away, the partial pressure is PA at point 2 is 0.2 atm. Calculate the flux of helium at steady state if the diffusion coefficient DAB of helium into nitrogen, right? So remember, we already discussed that AB here stands for helium into nitrogen is 0.687 times 10 to the power of -4, okay? And then the universal gas constant R is given as 82.057. So this is actually a hint for you, okay? So as usual, first of all, it is always recommended that you try to list down and label and try to draw all the information that you have, right? So for now, let's say that I want to list down all the information that I have. So first of all, I know that the temperature of the system is given to me. Okay, the temperature of the system, meaning that the temperature of the pipe is given to me as 298 Kelvin, and then the total pressure, right, 8 and 1 atm total pressure. So I can just write here P total is equal to 1 atm, right? And then we know that at point A, point 1, the partial pressure of helium at point 1, PA1 is equal to 0.6 atm. And then at point 2, we know that our PA2, the pressure of helium at point 2 is equal to 0.2 atm. And then I know that the distance of diffusion of helium into nitrogen is 0.2. So I can either say that my dz is equal to 0.2 meter, or you can always write that your delta z is equal to 0.2. Okay, it will have the same meaning, right? And then we are also given the value of our diffusion coefficient, DAB. DAB is equal to 0.687 10 to the power of -4 meter squared per second. Okay, and then the value of R is given as 82.057. So this is actually a hint for you guys. So before we try to solve the questions, I would just like to explain a little bit about this. So if you look at here, and remember, I've been telling you from day 1, and for this class it's also the same. Unit is very important. So that's why you have to know, that's why whenever you write, you list down all the informations, make sure you write the correct unit, right? So if you see here, our diffusion coefficient, right, the value DAB here has a unit of meter squared per second, right? So if you ask me here, meter squared per second is actually area per time, right? Because meter squared is a unit of area and second is a unit of time. But we are talking about diffusion coefficient. So if you see it in a logical way, we are actually want to see how fast helium is diffusing into M. So that is the basic understanding of when we say it's a diffusion coefficient. We want to see how fast is something happening. So basically, this meter squared per second is actually can be defined as how fast our gas or our diffusion is happening. Why? Because we can say that we can break down this unit into, first of all, we can say that how fast is our velocity, right? Meter per second is the unit for velocity or speed. And then if we know the speed, we also want to know how fast it is going. So that's why we have the meter here. So you can see here, if we separate this meter square into second into meter per second times meter, we can see that we want to know how fast our gas or our diffusion is happening and how far it is going. So here is the unit of speed or velocity, and here is the unit of distance. So if we combine, then we'll get a unit of meter squared per second. Okay, so that is how we define the value, a constant value of diffusion. Okay, so now we want to find the value of J helium, Ja, because we already labeled helium as Ja. So here you have a few options on how to solve these questions. So that is why in our previous class, I asked you, you must be able to derive from this initial equation, Ja is equal to negative dAB dCA over dZ into other form of equations. You can have it in terms of mole fraction, you can have it in terms of mass fraction, you can have it in terms of partial pressure, right? So you must be able to find this to actually convert this original equation into the desired equation. Now here, since I told you that we were given the value of R, and I know that if I am given the value of R, this is actually a hint that I might be able to solve this question actually by using our ideal gas equation, because the value of R is actually used in our ideal gas equation. So you have three options here. The first option is that you can use this equation. So you have to find, so if you look at here, this is the value that you want to find. This value is already given. You need to find the value of difference of concentration. The value of dZ is already given. So you need to find a way to find the value of Ca, right? That is the first option. The second option is that I can just convert this equation and I can write it in terms of partial pressure, dAB over RT dPA over dZ, right? So this is my second option, right? This is first option, this is second option. Or my third option is that I can write this equation in terms of partial pressure. So the same thing here, dAB PT over RT dYA over dZ. Okay, so this is my third option. So either option, whichever equation you want to use, you should get the same answer. Now, if you ask me, the easiest equation that I think I want to use is this one. Why? Because I already know the value of dAB. I already know the value of R, it was already given the question. I already know the value of T, right? The temperature of the system or the pipe. And I already know two pressure value at 0.1 and 0.2. So I can find the difference in pressure, and I already know the value of the distance, the difference between 0.1 and 0.2. So I can just use this equation. But if let's say you want to use this question number 1, so then if you look at question number 1, you have to somehow find the relationship between concentration and pressure. And then we have already looked at that. We know that PV is equal to nRT, and N over V is actually your concentration. So actually you can still use you can find the value of concentration based on the value of pressure and RT, which is similar. If you change the value of Ca, you'll get this equation. if you want to use the value of mole fraction, so you know that you can define mole fraction WYA is equal to either CA over C total, or in terms of pressure, we can also say it's equal to PA over P total. So you must be able to know how to relate all these three equations. Okay, so now I want to use my second equation. So I write here again the general formula. KA is equal to negative DAB dBA over dz, right? And when I substitute all the values, I know that, right, I have a negative sign here, negative 0.687. The unit is meter squared times 10 to the power of negative 4 meters squared per second. And then I have the value of R is 82.057 cm cube atm gram mole Kelvin times the value of temperature, which is 298 Kelvin. Okay, times the value of dPA. So remember, we have to make sure that we understand why we have the value of concentration. So here I will put 0.2 minus 0.6 atm, right? And then finally the value of dz is 0.2 meter. Okay, so when you solve this, you make sure that you will get, first of all, you have to know the unit of flux. So this is our molar flux. So for molar flux, we will have a unit of mole per meter squared second, right? So anyhow, after you have substituted all the values, you must get a value or a unit of mole per meter squared second. Okay, this is the unit of molar flux. So if you see here, the one thing that you have to be careful is that you have your cm cube here, and then everything else is in meter squared or meter. So you have to change first into meter cube. Okay, so you can try it on your own, and finally you'll get an answer of 5.62 times 10 to the power of negative 3 mole per meter squared second. Okay, so this is the final answer. So you can try using the other two equations and see whether you get the same answer or not.